Hi everyone, I am Dr. Kiran, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. So today we are going to discuss about capacitance of a diode. So PN diode can be considered as a capacitance. So let us see the overview of today's session. So first of all, we will discuss about the junctions of PN junction diode and capacitance of a diode, diffusion capacitance and transition capacitance. So it is CT, and conclude with summary. So let us first discuss the junctions of a diode. So PN junctions can be different types depending upon the junction concentration. For example, we have a step graded or LI or fusion or abrupt or non-linear junction. Step graded junction means what? So it is a non-linear junction. The carrier concentration in PN type, P type and N type materials are different. And similar to the next one is grown junction or linear junction. So in which the carrier concentration is uniform. So coming to the step graded junction. So here, for example, it is an N-type semiconducting material. So if you add any trivalent material to this N-type material, for example, this part I am adding with a trivalent impurity, then there is the concentration will be different. That means the concentration will be changes abruptly. That means N-type becomes P-type. So such a junction is called step graded junction or alloy junction or fusion junction or abrupt non-linear junction, because the carrier concentration is not uniform, non-linear junction. Okay. So whereas in a step graded or grown junction, the carrier concentration will be uniform. Okay. So based on this data, so we can now derive an expression for capacitance of a diode. So let us see what is capacitance. We know that capacitance means which stores electrical energy in the form of electric field. Okay, and it is also called as condenser, which will be used in fans. Okay, and then the expression for the capacitance is charge upon V, the electrical voltage potential applied and then charge. So where Q is what? Charge stored in the capacitor, and V is the potential difference between the terminals. Okay, so we know that. So this is a, for example, parallel plate capacitor. So this is a parallel plate. So this is one conducting material and this is one conducting material. Okay, so we know that the conducting material can allow flow of electrons and current will flow through these conducting materials, whereas in between these two plates there is a material called a dielectric material. Dielectric material which opposes the electric current through it. So here what happens, it opposes the electric flow, but there is a chance of electric field at these two plates. So electric field will be developed. So this kind of capability of a material is called capacitance, capacitance of a particular material. Okay. So in the same way, if you see the capacitance of a diode, so we have two types of capacitances which exhibits by the a diode, normal PN junction diode. So particularly the transition capacitance is observed in the reverse bias diode, and where it is also called it as space charge capacitance or depletion region capacitance, or many other names are there. And the expression for the transition capacitance is CT is equal to dq by dV. So where dq is nothing but change in the charge for the change in the applied voltage. So as I already told you that the transition capacitance can be observed in reverse bias diode. So we know that reverse bias, what is reverse bias? So P type and N type material are there. So P type is connected to negative of the battery, minus, plus, and N type is connected to the positive of the battery. So in such case what happens? The depletion width will be increased because whatever the positive holes are attracted towards the negative terminal of the battery, and electrons in this N type material are attracted towards the positive of the battery. In this case, the depletion width will be increased. So this depletion width will be increased. Okay, and this part, this P type material and N type material will act as a conducting plates of a capacitor, and in between there is a depletion region or transition region. The transition region can be viewed as a dielectric material because this area, this depletion region won't allow current to flow through this region. So it can act as an insulator or dielectric material. The space charge region between this P type conducting material and N type conducting material can be viewed as a capacitance. So it acts like a capacitor, PN junction. So this kind of capacitance in the PN junction diode is called transition capacitance because the transition region, the electric field developed at the junction, at the transition region. So therefore this kind of capacitance is called transition capacitance. It can also be given as by epsilon A by W. The transition capacitance can also be represented in this way because epsilon A by W. Epsilon A by W means, so what is epsilon? Epsilon is the dielectric material, that means the material or space charge region, and A is the area of the plates. A is the area of the plates and W is the width of the depletion region. Okay, and now let us consider a step graded junction. I am considering a step graded junction. So because we know, just now we have discussed the step graded junction in which the carrier concentration is not uniform, they are non-linear. Okay, so the carrier concentration changes abruptly, adding a small amount of a trivalent to a N type material. Okay, so by considering step graded junction, so the concentration will be like this. So this is a donor concentration and this is the acceptor concentration. See here, donor concentration, this indicates carrier charge density, you can say charge density on y axis. Okay, on x axis I can say this is the width of the depletion region of in the acceptor, that is N side or P side. Okay, and then the width of the donor, that is P side, will be very less because here the acceptor concentration is less. Here the consideration is acceptor concentration is very less compared to donor concentration. So here donor concentration is more, whereas here acceptor concentration is less. So in such case what happens, the depletion width occupied by that less carrier concentration will be more. That means this WA is greater than WD. Okay, so this the depletion width occupied by this acceptor carrier concentration will be more and compared to the donor concentration. So this is like a step graded or alloy junction. So in this case, now according to Poisson's equation, so let us derive the expression. Coming to the Poisson's equation, which relates the charge density with potential, charge density with potential. So which is given by d square V by dx square. So this is x Okay. So the concentration changes towards the x like this. So d square V by dx square is equal to q Na by epsilon. So where q is the charge on each particle, that is charge density. QNA means charge density upon W. This is epsilon. Epsilon is the permittivity of the free space or dielectric material. So now let us see one. So this is the relation between applied potential, which varies with respect to the x, that is distance from the junction, and this is the charge density. Now let us integrate equation 1. If you integrate equation 1, what happens? dV by dx. So already one integration square is gone. So dV by dx equals to QNA upon epsilon into x, because we have integrated on right side. So that means integral dx will come. So integral dx means x. So now again integrate, this is equation 2, let us say. Now integrate equation 2 again. Integrate equation 2 again. So what happens? So here if you integrate this, whatever happens? So dx, integral du by dx into dx gets cancelled. So you will get finally v. V is equal to, if you integrate this, what happens? QNA upon epsilon, and integral x means what? X square by 2. So therefore, but at x is equal to w. So at x is equal to w, what happens? Total width of the depletion region. So that becomes, the potential V becomes VB, barrier potential. So therefore, this can be written as VB is equal to QNA upon epsilon. What is x? At x is equal to w, I said. So w square by 2. Now let us differentiate this expression 3. So now differentiate this expression 3. So if you differentiate equation 3, what happens? With respect to V, equation 3 with respect to V, applied potential V. So in such case, dV by V means what? 1. So here QNA upon epsilon is constant, and this is 2W by 2 into dW by dV, because W is the variable here. So we are differentiating with respect to V. So therefore, we will get QNA by epsilon 2W dW by dV. So 2 gets cancelled here. So now what happens? I want this dW by dV. So why? I will explain later. So dW by dV value becomes 2 gets cancelled, epsilon by QNA into W. So let it be fourth expression. Okay. So now let us talk about the total charge at the junction. So total charge at the junction is given by Q is equals to total density, total charge density into charge on each particle. So this can be written as acceptor concentration into area of the plates into width of the plates into charge is Q. Okay. So this is Q. Q is equal to this one. So now let it be fifth equation. So now differentiate with respect to potential V again. Differentiate with respect to V. So if you differentiate this, you will get dQ by dV is equals to NA into A into W dW by dV, because we are differentiating with respect to V into Q. So what is the value of this dW by dV? So from fourth equation, so let us substitute this. dQ by dV is equals to NA into A into dW by dV means what? Epsilon by Q NA into W into Q. So NA gets cancelled, QQ gets cancelled. So finally dQ by dV, which is equals to transition capacitance, equals to epsilon A by W. So this is the final expression of your transition capacitance. So this way you can able to derive the expression for capacitance. So transition capacitance particularly observed in reverse bias condition. Similar to this, we can also find another kind of capacitance in a PN junction diode, that is called diffusion capacitance. So this is observed particularly in forward bias condition, and it is also called as storage capacitor, and the expression for this is CD is equal to change in charge by change in voltage. That means the change in the applied charge for the applied change in the voltage. So therefore this can also be treated as like this. So I have a PN junction diode, P type and N type. So I have connected in positive forward bias condition. P type is connected to positive and N type is connected to negative. So this is in forward bias condition. In such case, what happens? The depletion width in forward bias, we know the depletion width is decreasing. The depletion width is decreasing means, but the only immobile ions will oppose the flow of further flow of the charge carriers from P to N side and N to P side. Okay, the minority charge carriers concentration also improves in this. So whenever the depletion width, so there is a slight depletion width is there, and the charge carriers will diffuse from P to N side and N to P side. So then in such case also there is a capacitance effect is there, that is called diffusion capacitance, and this diffusion capacitance can also be represented as a CD is equals to I into tau by eta Vt. So how to get this? The diffraction, we know that Q is equal to IT8 tau. Okay. So what is I? I is the actual current flowing through the diode. So therefore let us write the current expression in this, that is I naught into e power V by eta Vt minus 1. Now let us differentiate this Q with respect to applied voltage V. So in such case what happens? Into tau is there. So this can also be written as integral I naught into tau e power V by eta Vt minus I naught into tau. Okay. So in such case, first of all let us rewrite this. I naught into e power V by eta Vt into tau minus I naught into tau. So if you multiply all this, so final expression is this. Now differentiate this dq by dv. So we have I naught e power V by eta Vt into tau e power V by eta Vt. We are differentiating with respect to V. So 1 by eta Vt will comes, and into tau is there, and this is constant. Differentiation of this is 0. So therefore we can write I naught into e power v by eta Vt upon eta Vt into tau. But we know that I naught into e power v by eta Vt. So can also be written as I plus I naught into tau by eta Vt. But we can neglect I naught. I naught is very less compared to actual current. So we can neglect I naught. I naught can be neglected. In such case, what happens here? dq by dv, which is equals to diffusion capacitance CD, is equals to I into tau by eta Vt. So this is the final expression for diffusion capacitance, which is observed in a PN junction diode when it is connected in forward bias condition. Okay, so you can expect small kind of questions, numerical problems on these two expressions. Okay, so that's all about for today's session. So today we have discussed what are the different junctions we have, that is step graded junction, grown junction, LI junction, like that, and then non-uniform junction or non-linear junction or grown junction. We have already discussed all these. And then diode has a capacitance. So we know that we have two different kinds of capacitances can be expected from a PN junction diode, particularly diffusion capacitance, which is observed in PN junction diode when it is connected in forward bias, and transition capacitance we have observed in reverse bias condition. And what are the expressions for this we have discussed, and what are the expression we have derived an expression for the diffusion capacitance CD, and we have derived the expression for transition capacitance CD. And if time permits, we will do some numerical problems in the next session. Otherwise, we will continue with next topic will be equivalent circuits of the diode. Thank you.